Hello students, good morning, good evening and good night depending on which time we are going to observe this lecture. Welcome to the 10th lecture and that is the last lecture in the solution chapter. In this lecture we are going to discuss the abnormal molecular mass. Before going to discuss this relevant topic, let us have a recap on the previous 8 lectures, what we have so far studied or we can say learned. The lecture number 1, we have discussed about the very fundamental and basic thing in solution chapter. That is, what is solution? Solution is basically a homogeneous mixtures of 2 or more than 2 components. But here in your syllabus that we are only concentrate on the solution which is having only 2 components, that is the binary solutions. Secondly, we have discussed about what is solvent, what is solute, and how the phase of the solution has been determined. It is basically the phase or state of the solvent, because solvent is the larger component in the solutions. So accordingly, we have discussed about different type of solutions like solid solutions, liquid solutions and gaseous solutions. And in that solutions also we have sub-classified with respect to the different type of solid, that is the liquid and gas and solid. Also we have discussed in that lecture that how do we able to express the concentration of the solutions. There are different ways that you can able to express. That is, first you can able to express in terms of percentage mass or percentage volume. Secondly, the most popular things and day-to-day basis we will use it, that is the molarity, then molality, then normality, then ppm, parts per million, and mole fractions. All those ways we can able to express the concentration of the solutions. So in this first lecture we have discussed all these things. In the second lecture we have discussed about some relationship like between the mole fraction and the molarity, mole fraction with the molarity, and mole fraction with molality and molarity. All these 3 basic relationships we have discussed, and it will be helpful to you in the solving different type of numericals in your board exams or all the exams that in the N90 NEET JEE exams you will be able to solve it, and it will clear a lot of points in this concentration terms. Then in the third lecture we have discussed the solubility of the solute in the liquid. Like in this lecture we have discussed about what is the factors, what are basically the factors that is going to influence the solubility of the solid in the liquid. As for example, that is the temperature, pressure and type of solvent, type of solute, that we have all discussed in detail. In the lecture number 4 that we have discussed about another very important thing, that solubility of the gas in the liquid. Different type of factors we have discussed, that is type of solvent, type of your different type of other things that we have discussed, and also this important part that we have discussed, the Reynolds law. This as far as this, how the solubility of gas depends on the pressure of the gas above the solution, that we have discussed in detail in that lecture. The lecture number 5 we have discussed about the vapor pressure when the 2 components are volatile components. At the time we discussed, we understand how mole fraction of those components in the solution is going to impact the solubility, going to plus the vapor pressure of the solution. And in this regard, we have discussed the Raoult's law. In the sixth lecture, we have discussed about the different types of solutions in terms of your Raoult's law. That those solutions which are going to follow the Raoult's law, this will be termed as the ideal solutions, and those solutions which are not going to follow the Raoult's law will be non-ideal solutions. And these non-ideal solutions will going to produce the azeotropic mixture that is also discussed in this lecture. In the seventh lecture, we have discussed again a very important and interesting thing, that when we put some non-volatile substance in a volatile solvent, at that time the vapor pressure of the solvent is going to be reduces. And this reduction in the vapor pressure of the solution, all these type of solutions, going to impact different properties of the solutions, like your boiling points, like freezing points, all the things that we will discuss in this lecture. In the lecture number 8, we have discussed about how there is a elevation of the boiling points when in presence of non-volatile solid. In the lecture number 9, we have discussed the depression of the freezing point of the solution, also the osmotic pressures. That is all in your lecture and your syllabus that we have discussed in all the 9 lectures. Now it is the last lecture and it is the 10th lecture. In this lecture, we are going to discuss again an important thing, that is the abnormal molar mass. So in this lecture, we will going to discuss the abnormal molar mass. This is K. Mukherjee in the Science with Mukherjee Sir YouTube channel. What do we mean by abnormal molar mass? Let us understand. From the elevation of boiling point, this type of collegiate properties or depression of the freezing point, we can able to calculate the molar mass of the solute. And this formula is normally that you can recollect in your lecture number 8 and lecture number 9. We have discussed in detail about this. That this is the formula by which we can able to calculate into suppose the molar mass of the solute. So we can equate this this is the molar mass, and this is the constant boiling point elevation constant, and this is the amount of the solute has been put into this solution. W1 gram is the amount of the solvent in kilo, and delta TV is your elevation of the boiling point. From this, you can easily able to calculate the M2 if we know all those parameters. This can be Kf also, Tf also, that the delta Tf, that is the depression of the freezing point. From this, we can able to calculate the molecular mass of this solute. But problem arises that for some solute that which is going to dissociate, as for example ionic solid, and for some organic solvent, organic solute like ethanoic acid, benzoic acid, those acid will be associate in presence of the benzene. So for those, if we calculate the elevation from the molar mass from this elevation of the boiling point or the freezing point, we will not able to calculate it rightly. How it is so? Let us understand. Suppose we have taken 1 mole of KCl solution. KCl in 1 kilo of water. So what will happen? Because of the fact it is a iodic compound, so this KCl will be dissociated into the K plus and Cl minus. So 1 mole of KCl, you can see it will produce 1 mole of K plus and 1 mole of Cl minus. So in the solution you will find, instead of 1 mole of particles, you will observe 2 moles of particles, because 1 mole of KCl, K plus and 1 mole of Cl minus. So there is a 2 moles of particles in that solution. Now 2 moles of particles, because we know colligative property depends on the number of particles, not on the nature of the particles. So we can, when we measure this colligative property, that is a depression of the freezing point, of elevation of boiling point, it will be observed that delta TB will be 2 into 0.52 Kelvin for this 1 mole of KCl, that is it will be 1.04 Kelvin instead of 0.52. If you calculate from the 1 mole of the, suppose you do not know whether it is dissociated or not, for that time you will wrongly, we will say that it's a calculated elevation point of the elevation of the boiling point will be 0.52, but actually we will calculate experimentally and we will observe this is because there is a dissociation of the ions. So when we calculate the molar mass from this elevation of the boiling points, which is observed experimentally, at that time we will find, because this M2 is directly inversely proportional to the delta TB. So we will get the molar mass, that will be half. We will get the half of the actual molar mass. Because of this fact, the colligative, there is a increase of the colligative property. Because delta TB we will find it is actually higher than what it should be calculated. So in this case we will find that whereas the KCl should have the molar mass 74.5, it will be coming around 27.25. So we can understand, for those solute which dissociate in the aqueous solutions, which is from that elevation of the boiling point, when we are going to calculate the molar mass, what we will find? We will find there is a wrong observations, wrong calculation, wrong determination of this molar mass, and it will be less than the true value. And another case, when there are some compounds, organic compounds like ethanoic acid, or you can say acetic acid, it will be dimerization. There is a process of dimerization is occurred. The 2 molecules of acetic acid will produce a dimer compound. This will be dimer. And how this is dimerization? Because there is a hydrogen bonding with this, that we understand now. So you can see this is the 2 molecules of acetic acid and their hydrogen bonding between these 2 molecules, that is the hydrogen bonding and this is the hydrogen bonding. So in presence of benzene, which have a very low dielectric constant, it will become dimer. Dimerization is occur. So in this case what we will find? We will find there is a reduction of the particles. The number of particles will reduced due to this process, dimerization process. And in this case, what will happen? That delta TF or delta TB, if we calculate from this experiment, from this case, what will find? Now what will find? You will find where delta TB is decreases. At that time, we will find the molar mass will be higher than the true value. So this type of things, that when we observe when we calculate the molar mass from the experimentally from the colligative property, it will not comes out to be the same as expected theoretically, and it is said to show a abnormal molar mass. In case of dissociation, it will show the lower molar mass that we observe in case of KCl, and in case of association, we observe the greater molar mass in case of ethanoic acid or benzoic acid, you can see. So this is a very, very important thing that we need to understand. So when we are going to, for those solute, actually we will not able to calculate the molar mass directly. So for that, to account these things, association and dissociations, or we can say degree of association or degree of dissociation, Vant has proposed one factor which is called Vant factors. In the year 1880, this is called the Vant factors. Vant factors, and it is represented by I. What we called this I is basically the normal mass, normal molar mass divided by abnormal molar mass. Normal molar mass divided by abnormal molar mass, and this will be, we can write in different ways. Let us understand. This, again we are writing this I, the Vant factor is equal to the normal molar mass, divided by abnormal molar mass, normal molar mass. This is equal to, again we can correlate this with the colligative property also. Colligative property, that is observed colligative property, observed colligative property, observed colligative property, observed colligative property, that is delta depression of the freezing point or depression of the elevation point, and the calculated colligative property. Calculated colligative property. Because we can understand that is the inverse relation between the colligative property and the molar mass that we have also observed in the formula. So due to this, there is a inverse relation, and this is further you can write total number of moles of particles before, after dissociation or association divided by number of moles of particles dissociation and association. So this is the Vant factors you can observe. And for KCl, when there is a dissociation for KCl, when there is a dissociation for dilute solution, we will find I is equal to 2. For acetic acid, CH3COOH, this I will be half. When we consider that fully dimerization is occurred in case of acetic acid, and for KCl there is a full ionization has been occurred. For that case, we will find this. So now, what we have to do? We have to now modify the formulas. The formula for the elevation of boiling point, or freezing point, or relative lowering of this, and also osmotic pressure, we have to modify it. So, what will be the modified formula? Let us understand. Now, this formula, the first formula, that is relative lowering of vapor pressure. Relative lowering of vapor pressure. That we can modify this equation like this. P, that is, we already understand from our previous lecture that we have discussed in the lecture number 7. I into X2. X2 is the mole fraction of the solute. Mole fraction of the solute. So you have to put this I into factors. This is relative lowering of the vapor pressure. And second, that elevation of boiling point, elevation of BP. Elevation of BP, in this case you will find is again delta PB is equal to KB into W, KB into W2 by W1 into 1000, and molar mass M2. So you have to put also I here also. Now about before formula without I, now Vant factors have been included. For elevation, for depression of the freezing point, depression of freezing point, that is delta TF, you will get I KF W2 by W1 into 1000 into M2. And fourth, that is the osmotic pressure. In case of osmotic pressure, that we know that phi is equal to I into N2 by V2 into I. So this is the osmotic pressure. There is a Vant factor. So in the formula you have to include the Vant factors. So you understand the abnormal molar mass. It is basically due to the behavior of the solute particles when it dissociate or when it associate. It will going to show a abnormal molar mass which is not actual, which is basically the due to the presence of the high number of particles, that there is a difference, there is a variations in the colligative property, and from that when we calculate we will get a wrong result, that is not a true value, but this is called a abnormal this. And what is abnormality, that we understand. Now we are going to discuss from this we can able to calculate the degree of dissociation or degree of association. That we will now discuss. We will discuss the degree of dissociation, degree of dissociation, that is calculation of this degree of dissociation. And suppose here one molecules when dissociate produce n molecules. Produce n molecules or ions. You can produce n molecules or ions, suppose. And we have taken 1 mole. This reaction will be this is a suppose of the substance A. This is the substance A. So this will be A n into P. Initial 1 mole of substance we have taken. At equilibrium it will be 1 minus alpha, because this is we have taken degree of dissociation is alpha. So 1 minus alpha and it will be n alpha. Very simple. The total numbers of particles. We can write total number of particles is equal to 1 minus alpha plus n alpha. So Vant factor is know I is equal to total number of particles, that is given by this, divided by 1. Before the total number of moles of particles, before it will be total numbers of moles of particles. You can write total number of moles of particles after the dissociation, and this will be coming out this. And so we calculate it, we can see I is equal to 1 minus alpha plus n alpha, and we take this I here, I minus 1, that will be n alpha minus alpha. We are taking this and it will be coming around I alpha. We have to calculate the alpha. Alpha is I minus 1 divided by n minus 1. So n, what is n here? N here number of ions produced. Suppose BaCl2, suppose. For BaCl2 we know that this number of ions produced is 3. Here number 1 and 3. So n is will be 3. So if we know the Vant factors and if we know the n, then we can able to calculate the degree of dissociation. Okay. Similarly, we can calculate the degree of association. Degree of association. There are some molecules have a tendency of association between the hydrogen bonding that we have discussed in case of ethonic acid or acetic acid and benzoic acid. So in this case, we understand the n molecules of substance A. n molecules of substance A form an molecules. And we have taken, suppose this reaction will be this A is A. So we taken 1 mole of this A initial, this same thing, that is initial, and after the association you will find at equilibrium it will be, and degree of association, suppose this is alpha, and we have taken 1 mole of substance. So at equilibrium it will be 1 minus alpha and it will be alpha divided by n. So at total moles of particles will be this 1 minus alpha plus alpha by n. And we know Vant factors I is equal to 1 minus alpha by n divided by 1. We have taken before the association it was 1 mole. So you can see I is equal to 1 minus alpha by n. We will y minus 1, that will be coming around alpha by n minus alpha. So we can write this, we can write alpha is equal to I minus 1, that will give in alpha 1 minus n this. So we can write alpha is equal to, now we can write here alpha or degree of association that we can get 1 minus I into n divided by n minus 1. So this is the degree of dissociation and this is a degree of association. That we have, after putting the minus value here, we will get this 1 minus I, and here in the denominator we get, this is basically 1 minus n, that will be coming to n minus 1. The n will go to this here. So it will get this. So now we understand that how we will calculate the degree of dissociation and degree of association for these cases, and with respect, with including the Vant factors. So that is all for this chapter. In this chapter total we have 10 lectures to cover all the points. Hope all the things has been clear to you. If you have any doubt, you can comment in the comment section. And that is all for today's lecture. If you like this lecture, thank you very much for watching.